The test for exactness is this. The ODE is exact if and only if the following thing is true. And this is something you're going to use a lot. The partial derivative of m with respect to x has got to be equal to the partial derivative of n with respect to t. And you know what? There are proofs in different differential equations books that will prove to you why this is the case, why this is the test for exactness, and why if and only if it has to be true. I could, show you that here, but in all seriousness, it's going to take us on a detour to prove to you that this is true. And the detour isn't really that valuable because most importantly, what you really need to do is learn how to apply it, in my opinion. You could certainly look in a book and they would show you why this has to be true. But from your point of view, what you need to really understand is that when you're confronted with a differential equation, you're going to have an m and you're going to have an n. And you need to take these partial derivatives and see if they're equal. And if they are, then it's exact. And then you can try to find the solution to the, to the equation. But if it doesn't equal, then you can just stop and say, well, forget it. I'm not going to go any farther because it's not going to actually work out. So the real trick in this whole thing, once we figure out that it's exact and once we really try to go about doing it, is trying to figure out what f is. So this is sort of the general overview, general outline. And what I want to do next is start to apply some of this stuff. So let's say we have a problem, a differential equation, x times dt minus t times dx is equal to 0. And first, what we want to do for all these problems, we want to test to see if it's exact or not, and then if it is exact, solve it, and then of course if it's not exact, we can just stop. So first thing you know is you really have to compare it. We have a dt, we have a dx. This problem, I've written it this way, but this problem could have been, dx, well, you know what, let's do it. Let's move this guy over here. We'll say t times dx is equal to x times dt. And so if I move this guy over, t dx dt is equal to x. And if I move the t over there, dx dt is equal to x over t. So you see, there's the original differential equation that we really have there. And it might be given to you this way, but when you rearrange it, you're allowed to write it into this form, which we know is exact. The only reason I'm really showing you this is because sometimes you're going to have differential equations written in a form that doesn't look exact, but whenever you beat it into shape, you can actually make it look, and to be in the proper form. All right, so the first thing you need to do is we want to identify that it's of the proper form. Now, everything in front of the dt is going to be m, and everything in front of the dx is going to be n. So what we're really trying to test to see if this is exact is the partial derivative of m with respect to x is equal, question mark, to the partial derivative of n with respect to t. And just to be absolutely clear about it, I'll write it right over here. The function m is equal to x, and the function n is equal to negative t. The function n is equal to negative t. In fact, I always recommend you writing m and n like this because it'll really help you focus on what you're trying to do down here. Now, what is the partial derivative of m with respect to x? That's just going to be 1. This guy right here, with respect to x, equal, question mark. Partial derivative of n with respect to t. This is n with respect to t is negative 1. Are these two guys equal? The answer is no. So because 1 is not equal to negative 1, this is not exact. And what does this mean? This means that even if I go and try to find out what function f is going to satisfy all this stuff and actually go down through it, I will not be successful. I will not be able to do it. It won't be a matter of the calculus. It'll be a matter of f doesn't exist. You won't be able to find an f to satisfy these partial derivatives. So this constraint right here that we're talking about, partial derivative of f with respect to t is m, and this one is this guy right here, you won't be able to find an f that's going to satisfy that. And that's really what it's going to boil down to. So let's go in the next problem and test and see if the next guy is exact, and if it is, we will solve it. So the next problem is t times dt plus x times dx is equal to 0. Now first notice, it is in the form of the form of our equation that we care about, some function in front of dt plus some function in front of dx. And if you remember back, the guy that's in front of dt is m. The guy that's in front of dt is m. So this is m, and this is n, okay? And the constraint to test if this is exact is, so let me write this down, m is equal to t, and n is equal to x. And the constraint is the partial derivative of m with respect to x equal to the partial derivative of n with respect to t, okay? One way to remember this constraint, to memorize, doesn't really help you prove it, but one way to remember it is m is always the function in front of dt. So for your constraint, you're taking partial m with respect to the other variable, dx. N is always in front of dx. So in your constraint, to test it, you're taking partial n with respect to dt, which is the other variable. So it gets confusing because you might start taking the partials with respect to these, but you have to remember to take it with respect to the other guy. All right? So what is partial m with respect to x? That's 0 because there's no x in here at all. Okay, what is the partial of this with respect to t? Well, that's also 0. So yes, it is exact. So what this means is, because it's exact, is we will be able to find that master function f that satisfies everything else. Okay.